So anyway, the last kita today is on heat. Okay, heat and temperature, energy in the form of heat. And supposedly kita patut cover thermodynamics juga, but if you look at our my teaching plan, okay, yang I share in the first class hari tu, so actually for thermodynamics we can cover in 2 weeks. So rasanya memang ikut yang tu lah, sebab we see how it goes, okay, tengok progress macam mana. But don't worry, hari ni punya slide pun tak banyak, hopefully. Okay. So, sekejap saya nak tengok ada dekat waiting room. Okay, sorry lah siapa yang tertunggu dekat waiting room sebab perasan kadang-kadang. Okay, we start with the heat and temperature, alright. So basically, I know that this is very general, rasanya semua orang dah tahu. Okay, but of course, refresher as usual. Temperature. So temperature is actually a measure of the average kinetic energy of individual molecules. So thermometer, the one that we use nowadays kan, COVID, so di mana-mana pun we have to check our temperature. So temperature ni, thermometer bila you check your temperature, is actually a measure of average kinetic energy because all molecules, all atoms, they vibrate. Okay, at any state, tak kira lah at solid state, liquid, ataupun gas form. All are vibrating. Okay, so kalau you tengok materials yang cold, okay, even ice, kalau at the atomic level, they are vibrating. Okay, that's why you are able to measure the temperature. Because that vibration, okay, vibration bila bergerak, it's kinetic energy kan? So the average kinetic energy tu is something that you can measure. Okay, so whole materials, when you heat it up, it becomes hotter. It is because the vibration is increased. Okay, it's higher. So you got an external heat, right? External heat, you heat it up, increase the vibration, increase the temperature. Okay, so heat is energy transferred from one object to another object because of the difference in temperature. Okay. And remember back yesterday about conservation of energy. So energy, the total energy of all these molecules is conserved. Okay, so this is what we call the thermal energy of that material. Okay, so just linking back to what we learned yesterday about the conservation of energy. Because remember, heat is also a form of energy. All right. So heat propagation. Okay, this one, this more dah hafal. Ada 3. Remember, convection, conduction, radiation. Okay, very general theory. Okay, I know. Tapi tak apa, kita tengok. So heat migrates from a heat source, okay, higher temperature, to a heat sink, which is at a lower temperature. So this always happens. If you look at, things that is happening in front of your eyes, dipanaskan air, right? So temperature, the heat will always migrate from higher temperature to lower temperature. And this is related as well if you look at what is happening at the coastline, okay, antara the ocean and the landmass. Okay. So why is there wind? Why is there convection? Because there's a temperature difference between these 2 areas. Okay. So conduction is heat. Okay, heat is the vibration of particle. And a particle in a state of vibration communicates its motion to neighboring particles. That's why bila you pegang periuk ni, you can feel the heat. That's me. And convection, of course, the flow that you get. Okay. So siapa yang masak, sebenarnya you boleh perasan bahagian atas ni is actually the highest temperature. Okay, the liquid at the top is always ones that are at the highest temperature. Okay. And lastly, radiation. Radiation ni biasalah. So kalau you pergi camping and you buat barbecue ke, you have fire, kan? Then malam-malam contohnya, it's cold, so you build up a fire and you get that heat. Okay, that is through radiation. Okay, right. Now we talk about temperature and we talk about heat. So what is specific heat? Specific heat ni is actually the amount of heat required, okay, and this can be added or removed because if you look at reaction, it can be exothermic or endothermic. Okay, we call back apa dia exothermic, apa endothermic. This one we will cover next week when we look at thermodynamics. But just as a basic thing to look at. Okay, so when you add or remove the heat to change the temperature of a given material with mass m. So this is the equation that is related to that, right? And easier to understand if you look here, dekat table ni, specific heat, every, basically all materials, it has its own specific heat, okay? So contohnya, paling easy lah, if you look at water, okay? Kita water kita simpan kejap lagi. So copper and glass, okay? Copper ni, if you look at that, the specific heat is much lower, okay, than glass. Kenapa? So because kalau if you heat up these two things, okay, at the same mass, so let's say you ada 1 gram of copper, 1 gram of glass, lepas tu you heat it up. At the same amount of time, okay, copper is gonna get hotter much easier, okay, much faster, much easier, because it has specific heat yang rendah. Okay, that's why kalau masak, okay, hari ni punya terminology is masak. Kalau you masak, kenapa a lot of cookwares are made from, ada yang made from steel, ada made from aluminium, made from copper, okay, because these things can be easily heated up, all right, and things that can be heated up easily is cooled down easily as well. So the rate of heat added or removed to is related to that. Kalau rendah, then it's easier to heat it up and cool it down. Okay, so as you go along, you akan jumpa benda yang much higher. So here, if you look at water, okay, water sebenarnya tinggi. Okay, you require a lot of heat actually to heat it up. So at a specific mass, right, let's say 1 gram, and you want to heat it up 1 degree Celsius, okay, you require this much heat. Okay, that's what it means, by the way. But another thing that is interesting about water, okay, kalau you nampak kat sini satu kan, this is 1. So here, calorie. So calorie is actually a very common unit for heat, okay, especially if you look at, the nutrition labels, okay, all of the things, the food that you eat, usually they have this nutrition label outside, right? And it is in usually it will have calories here. Okay, so basically calorie, what is it? It's the amount of heat necessary to raise the temperature of 1 gram of water by 1 degree Celsius. Okay, ingat tadi yang ni is 1 kan? So that's why the convention is you say 1 calorie is because you want to raise the temperature of 1 gram of water. Okay, it's related to water because it's so much easier. People can definitely relate to water, okay, compared to mercury. it's not easily available, kan? So with water, people can understand it more, the public can understand more, right? That's why we use calorie as one of the most common unit for heat, right? So this is calorie. Calorie is 1 gram by 1 degree Celsius. But usually the unit is kilocalorie, KCAL, right? And sebenarnya, if you look at the labels, calorie ni is not this one tau. It's kilocalorie. Okay. Calorie, so jangan tertipu. Kalau you tengok dekat you punya air tin ke, water, soda water, tengok kat luar calorie kan, and you count that as 200. So actually this is kilocalorie. Right? Perasan tak? Ke semua orang tahu ni?
Doktor saya perasan.
Perasan That's good. So memang kira kalori, that's why you understand. Okay, there's something yang I just want to highlight. Sebab, okay, sebenarnya people might say, oh ni tipu ni. But it's not, okay. So usually kalau C besar ni, if they use caps, okay, for C, it means kilocalorie. So there's no attempts to lie or anything with the companies, big companies tak ada pun. Okay, so if they use big C, then it means kilocalorie. Okay, so I just put in BTU sebab this is a British Thermal Unit. So it's not an, if you look at reference books, then you might sometimes find BTU as well, right? And that is related to 1 pound of water and raised by 1 degree Fahrenheit. Okay. Now, to put things into perspective, tadi kita tengok Coca-Cola kan? So here, so there used to be this work it out calculator, right? And this is UK punya Coca-Cola. So they developed this calculator. I know that now there are, you know, a lot of different apps to do this, but this was in 2012. And they developed this, and you can actually look at what are the types of Coke out there. Okay, ada Coca-Cola, Coca-Cola Cherry, and then what type of workout that you have to do to burn this calorie. Okay, so this is related to nutritional and health as well. Okay. So if you look here, 1 can of Coke has 139 calories. So this is actually kcal, right? So you can think about that. 1 tin of Coke, okay, so actually you need the energy contained in there, you can heat up 139 kilograms of water to 1 degree Celsius. Or another way to look at it, you have around 13.9 kilograms of water, you want to heat it up for 10 degrees Celsius. Banyak tu, right? So we can imagine then why, you know, obesity is increasing, right? Because, you know, people took an excess of calories, okay? And we don't really burn it off, right? So for those, okay, this is not preaching or anything. So we have to go for an active lifestyle. Okay, guys, just to selingan je ni. Okay. Okay. Another thing about calories, so this is about the mechanical equivalent, because usually, of course, calorie is one of the things usually used, right? But usually in scientific books or references, we use joule for energy, remember? So this is the how you can look at the equivalence of that. So the relation between joule and calories, kilocalories, and BTU. Okay, just to aid you in any calculation whatsoever. in the future. Okay, so now, amount of energy in food. Okay, you look at what we eat every day. Okay, so sebenarnya there's a lot of energy contained in that. Okay? And this is the energy contained. And if you want to burn it off, okay, the calories, you can look at how much calories burned off with what type of activity that you're doing, right? So this is just to highlight, okay, the more intense an activity is, the higher calories are burned, okay? It is, you know, it's logical, of course, if we think about yesterday as well, power, okay, in relation to energy, when you do something that requires requires more work, okay, more power is required, right? And that energy must come from something, right? And again, one more thing, average energy costs for different activities for a normal 20 to 30-year-old man. So usually for men and women, there's some differences, okay? So this is one example. Here. So even at complete rest, okay, your body does burn calories. You know, even I think maybe you guys have heard as well, burning calories while sleeping. Okay, it's true. It's not made up. It's true. Because you know, in our body, if you look at our body as a system, again, I'm using our body as a system. There's a lot of things happening in there, right? You have a lot of things that your blood pressure is something that needs to be controlled by your heart, you know, the arm motion, any movement that you make, the muscles, you know, all of those need energy. Okay. So even while sleeping, the maintenance, the repair, the cells, it requires energy. So that's where, you know, the term burning calories while sleeping comes from. Right? So if you look at that as a system, okay, and you link that to how exactly this energy is generated, okay, and we look at oxidation of fat, right? And this is a representation of oxidation of fat in our body. Okay, so this is from a research done by, if I'm not mistaken, some researchers in Australia. Okay, back in, can't remember when, but it was fairly recent, I guess. So they calculated this basically, and you can imagine 10 kg. So if you lose 10 kilogram in weight, so where does that goes, right? So actually, around 8.4 kg of that is CO2. So when you breathe out, right, that CO2 is actually your body weight loss, right? And the rest of that is water. So this water can be in the form of sweat, you know, in your blood, your feces, urine, and all of those waste materials that you expel from your body, right? So it's water and CO2, okay? And if you look at that, right, and that is our body as a system. But what about when you want to generate energy from fuel, right? And this is related to combustion. Okay, so combustion is essentially the same thing because this is oxidation, and oxidation is you know, one part of combustion as well, right? The theory is similar. So you have your fuel here, okay? So imagine you are burning something. So look at your car, for example. So the fuel, the gasoline that you have in your car, you know, is burned, okay? And you generate CO2 and yes, water as well, because combustion is happening inside your engine, right? And you generate the energy required to move the car. Okay, so if you look at that, it's easy to understand because that is using car, right? And if you look at electricity generation, of course, electricity that is based from combustion or something. So usually in power plants, okay? So this is not related to more renewable energy such as solar power or wind power where you don't do combustion per se, okay? Not all the time. But with power plants, the common power plants that we have right now, that is depending on coal, on gas, right? So what they do to turn the turbine is they combust that fuel, okay? So imagine that fuel is anything. It can be coal, it can be petroleum, you know, and you can relate that to all sorts of different systems where you can generate something based on combustion, right? And that is what we are going to look at when we study about thermodynamics next week, right? So before we look at fuel, okay, like I mentioned before, okay, we look at systems first. Okay, I know we've touched a little bit on this. Was it yesterday or the week before? Okay, so we have system, right? So system, it can be open, it can be closed, and it can be isolated. Okay, there's three different situations, right? In an open system like this, when it's not being plugged, for example, yeah. So mass and energy may enter or leave the system. Okay, so imagine if this is hot, right? And you know, steam is coming out. So mass is coming out and energy as well, because when you touch the glass here, you can feel the heat. Okay, that is an open system. With closed system, so imagine you plug that glass tube, for example. Okay, the mass cannot enter or leave, but still the energy can. Okay, so if you hold it, you can still feel the heat, right? But the steam will not go out. So there's no mass transfer. But another level of that, if we put in some insulation, okay, it becomes an isolated system. So now if you hold this, this glass cell, for example, okay, you won't feel the heat anymore because the system is isolated, right? And in this situation, no energy may enter or leave the system. And, you know, because it's closed, no mass can enter or leave as well. And you can imagine inside, the heat will flow between different parts with different temperature. Okay, so there's no other ways of transfer. You know, it doesn't do, so you can actually have an isolated system. And this is very important because, you know, if you have a calorimeter, for example, sorry. If you look at calorimetry, it's a quantitative measurement of heat exchange. Okay, so imagine yang isolated system tadi. Okay, this is a very simple system, but we have now a water calorimeter. So in theory, it's the same with the isolated system that I showed just now. The only difference is that you can now measure, okay, the heat release. So what happens here is if you have some kind of sample here, okay, and you want to know, sorry, you can actually measure the changes in temperature, okay, in this way, because you can, if you have your sample here and you combust that, so you have oxygen here, okay, and combustion is happening, right? That heat, okay, will be transferred to the water that is outside here, okay? And remember, heat always flows from, you know, the higher temperature to the lower temperature. So definitely, if you heat this up, it becomes a heat source. Okay, and this is your heat sink. So the heat will move from here to here into the water. And you have your thermometer there to measure exactly how much the temperature change. Okay, what is the heat exchange in there, right? And this is an isolated system because you have your insulation here. So it's all of those is insulated. Okay, so in essence, in theory, the energy exchange is only happening here, but not from here to outside. Okay, and this is what we call our system. All right. So far, so good. Kenyang je semua orang hari ni.
Okay, Doctor.
Okay.
Yes, doctor.
Calorimeter. Anyone has ever used calorimeter before? Maybe tak ada kot. Tak ada
No.
No, okay. That's fine. Because maybe in FYP, maybe I'm not sure what you guys are going to do with your project, but if anyone is looking at, you know, combustion or fuel properties, okay, you might use calorimetry in the future. Okay. Right. So this is how you can measure that using this equation, right? So because you have your object is also considered your sample just now, okay? And you have your water and you have your vessel. So basically this is, again, it comes from the conservation of energy that we studied yesterday, okay? Because in an isolated system, it should be zero, all right? Because there's no energy transfer to outside of the system, okay? So that's why it's zero. And you can calculate the temperature change here, and eventually you will be able to calculate the specific heat of something, right? And we come to here, so bomb calorimeter. So actually, there are different types of calorimeter available, okay? And each type is used for different purposes, okay? Just now, we look at water calorimeter, and this is bomb calorimeter. So don't be afraid about the word bomb. So there's nothing, you know, hanky-panky going on over there. It's just that, it's called that because in this bomb calorimeter, okay, very similar setup like before with the water calorimeter. However, your container, your combustion chamber here is made from steel, so reinforced steel usually. So what is happening is that your sample here, okay, usually it is form of your fuel, right? Whatever fuel, whatever material that you want to test, we can test it here, right? So when you have the steel one, you want to, you know, do a complete combustion, right? That's why you need a very strong material for the combustion chamber. Whereas for the water, with one here, if you look, if you try to Google, there are even some that are made from styrofoam, okay? So you can imagine styrofoam definitely cannot be used for bomb calorimeter because essentially you are burning this up at a very high temperature. Okay, so you need to have material that can withstand such high temperature and pressure. Okay, but the theory is similar. So whatever changes in energy here in the heat as you are heating this up will be transferred to the water, and again the thermometer will you know, measure that temperature difference. Okay, and you can calculate the calorific value of your fuel. So kalau kat sini, your sample here, kan? So let's talk about some alternative types of fuel. Okay. So of course you can test coal, you can test gas, you can test different types of fuel here in the sample chamber, so or combustion chamber, right? But at the same time, let's say I'm not sure if you guys have ever heard about biochar. Ada dengar ke?
No.
Tak pernah. Ada yang yes, ada yang no. Okay, there are some, okay. Other than that, there's also charcoal, tahu kan? You pernah buat barbecue kan?
Tahu.
Kan? Okay. Okay, arang kayu tu, charcoal tu, there are, that one is made from kayu, okay? But there are also some alternative materials. Okay, for example, palm oil punya ni, palm fronds, or you know the batang dia tu. Okay, because Malaysia and also Indonesia is, these two countries are, you know, the highest producer of palm oil. Okay, so definitely we have a lot of palm oil waste. Okay, not only 10 years ago, people are looking at POME, okay, palm oil mill effluent, because that is the waste generated from palm oil mill, okay, when you want to extract the oil. So you have a lot of wastewater, okay, and this is, it has to be treated. So it can be used as something, and we will look at that in one of our lectures later on. Okay, but my point here is that with palm oil, okay, there's a lot of other waste from that as well. So we talk about agricultural waste. Okay, dia punya pelepah, dia punya batang, all of that can be used. And one of the ways to do that is, sorry, you can, oh, I don't know. Okay, sorry. So you can actually make that into arang. Okay, and this is used actually in African countries. Okay, because a lot of people over there, they don't have access to, you know, electricity. They don't have access to gas, for example. So they use these kind of alternative fuels, okay, to cook food, for example. So they don't have access to LNG yang kita ada dekat rumah tu, tong gas tu, they don't have that. So they have to look at different types of, you know, things that can be burned, right? So one of the things that they use there is oil palm fronds and oil palm bark, okay, all those pelepah, okay. So they use this to become the fuel for their combustion, right? And if you want to look at the calorific value, okay, calorific value is actually here. So you can think of calorific value as how much energy is contained inside that material, for example. So you have just now the oil palm fronds. Maybe you want to check the calorific value before you start to study the how you want to improve the burning of it, for example, yeah. So you can test that using the bomb calorimeter. So you put in your sample there, okay, you combust it, and you look at the temperature change, and you can calculate the calorific value, right? And you can compare that with what are the common fuels that we have right now, right? So, okay, before we go to the next slide, I will just read this one. So calorific value, so this is the actual definition, okay? The definition that I used just now is the layman definition. So calorific value is defined as the amount of calories generated when a unit amount of substance is completely oxidized. Okay, and its determinants in the bomb calorimeter. So that's what we were talking about just now. So the amount, a known amount of substance, that fuel just now, okay, it's burned at constant pressure and standard condition. Okay, and the heat release is captured in a known mass of water. Right. If the initial and final temperatures of the water is measured, the energy release can be calculated using this. Right. So that is essentially how you are going to calculate calorific values of different types of fuel. Okay, and you will get different different values for different types of material. Okay, so for example, if you look here, hydrogen actually has a very high calorific value. Okay, so it's actually, if you read my Padlet, okay, I highlighted hydrogen. Why? Because it's one of the type of fuel that I think is very good to be used. Okay, but of course, right now we don't really have the appropriate infrastructure for it. But if you look at Sarawak Energy, okay, Sarawak Energy has actually unveiled the hydrogen bus. Anyone from Sarawak here? Tak ada, semua kat Semenanjung kan? And Indonesia? Ha? Ada ke?
Desa from
Ada.
Indonesia, Doctor.
No one from Sarawak, tak apa. This is not, just want to ask what is happening over there.
Deshasa from Indonesia.
Yeah, me, Doctor Desa.
Desha, Desha, are you in Indonesia right now?
Yes, Doctor, in
Oh,
Indonesia,
okay.
Bandung.
Oh, Bandung. Okay. Interesting. Saya selalu nak pergi ke ITB tapi haven't got the chance yet. Alright, so tak apa. So I was talking about Sarawak Energy. So Sarawak Energy, okay, I think it's in 2018 or 2019, they unveiled the hydrogen bus. Okay, and they actually uses hydrogen for the public bus over there. So it's not throughout the whole of Sarawak, okay, because I can't remember which city, but you know, it's very interesting to look at how this technology grows. Okay, if it's there, then you know the potential is there. Okay, so compare that to non-fuels right now. Gasoline, we have diesel, we have coal, right? And a lot of different other things as well. Okay. Briquettes ni, ni lah dia. Briquettes ni, if you look at the previous example that I gave on the oil palm fronds and barks, okay, they can be made into briquettes. Okay, and they call it, it's very so it's quite high, it has quite a high amount of calorific value, but it depends on how you prepare the briquettes, right? Okay, so actually that is the last slide. Okay,